Have you ever just stopped and wondered how we got here? I mean, how did we get from a basic calculator to an AI that can write its own code, dream up new art, and actually start taking action in the world? Well, it wasn't some single eureka moment. Nope, it was more like a climb, a journey up a ladder of incredible breakthroughs where every single rung was built on top of the one before it. So let's start climbing. This whole dream of a thinking machine isn't new, not at all. It's ancient. It really starts way back with Aristotle, who was the first to formalize logic. Then you've got Ada Lovelace writing the first ever algorithm, and of course, the legendary Alan Turing giving us the theoretical foundation. But the real starting pistol for AI as we know it, that was fired in 1956 at the Dartmouth Conference. That's where the name artificial intelligence was officially born. Now, this right here is probably the single most important pivot in the entire history of AI. For decades, we were stuck on symbolic AI. That meant we were literally trying to hand-code every single rule about the world into a machine. If this, then that, it was fragile, It just broke whenever it saw something new. But then came the shift to statistical AI, and the whole game changed. Instead of telling the machine the rules, we just started showing it mountains of data and let it discover the rules for itself. That idea is the bedrock of everything we have today. Okay, so here's our plan. We're going to climb that ladder of AI breakthroughs I mentioned. Each rung is a huge innovation that cracked a problem the previous one couldn't touch. We're going to start with just learning simple patterns and climb all the way up to AI that can act on its own. All right, first rung. The first really big wall that early AI ran into was learning anything that wasn't a straight line. The textbook example is called the XOR problem. Basically, you just can't separate the data points with a single straight line, and for early models, that was a deal breaker. This problem was so tough it actually led to the first AI winter, a time when a lot of research funding just completely dried up. So, what was the solution? The multi-layer perceptron, or MLP, the first real neural network. And the big idea here was just brilliant. By stacking layers of these simple little neuron-like units, the network could learn to draw complex, curved lines to separate data. It's kind of like the difference between only having a stiff ruler versus having a whole toolbox of flexible curves. Suddenly, the impossible problems were solvable. So how does it actually work? Well, think about it like this. The input is just a bunch of data, right? Like the square footage of a house, number of bedrooms, etc. That data flows into the hidden layers. That's the process. And in there, the network learns how to weigh all those features. Maybe it learns that square footage is way more important if the house has lots of bedrooms. And finally, you get the output, a single prediction, like the price of the house. Simple as that? Okay, let's hop up to the second rung. So MLPs were cool, but they were basically blind. If you showed one an image, it just saw a long, flat list of pixels. It had no concept that pixels next to each other were related. To an MLP, a cat in the top left corner was a totally different object than the exact same cat in the bottom right corner. It just had no spatial awareness at all. The breakthrough for this was the convolutional neural network, or CNN. The input is still an image, sure, but the process is completely new. Instead of looking at all the pixels at once, it uses these little filters that slide across the image, learning to spot simple stuff first, like edges or corners or textures. Then, deeper layers combine those simple things into more complex shapes, like eyes or whiskers, until finally it can make a prediction. Yep, that's a cat. So AI could finally see, which was huge, but it couldn't really read. See, with an image, the order of things doesn't totally change the meaning. But in language, order is everything. A CNN can't tell the difference between dog bites man and man bites dog. And, well, that's a pretty critical difference, wouldn't you say? And this brings us to our next major hurdle. The third rung on our ladder is all about giving AI a memory. The first attempt at this for sequential data was the recurrent neural network, the RNN. It had this cool feedback loop, which let information stick around. But it had a fatal flaw. It was unbelievably forgetful. We're talking the memory of a goldfish. And this forgetfulness was caused by a nasty little thing called the vanishing gradient problem. Essentially, the further you got into a sentence, the more the information from the beginning just faded away. It's like a long game of telephone where the original message gets totally distorted. It made it basically impossible to connect a word at the end of a long paragraph back to a subject at the beginning. The solution was so clever. It was called the LSTM, or Long Short-Term Memory Network. The source material had this fantastic analogy for it. Think of it like giving the AI a notebook.
LSTMs have these special gates that control the notebook. The forget gate decides which old notes to erase. The input gate decides what new, important facts to write down. And the output gate decides what info is actually relevant to share right now. This simple idea finally gave AI a reliable long-term memory. So we fixed the memory problem, but now we had a new one: speed. See, LSTMs were powerful, but they were slow, painfully slow. They had to read text one word at a time, just like a person. And in the age of GPUs that can do thousands of things at once, this was a massive, crippling bottleneck. It was holding the entire field back. And then the revolution came. In 2017, a paper dropped with a really simple, almost cocky title: "Attention is all you need." It introduced the transformer architecture, and it completely threw out the slow, one-word-at-a-time idea. This paper, right here, is the moment modern AI was truly born.
So here's the absolute game changer. While an LSTM had to read a sentence word by word, a transformer looks at all the words at the same time. It processes everything in parallel. This meant we could finally unleash the full power of modern GPUs, training on way more data and with context windows that were thousands of words long, not just a few hundred.
And the result of that breakthrough was an absolute explosion in scale. I mean, just look at this progression. In 5 years, we went from models with around 100 million parameters to models with nearly 2 trillion. The transformer didn't just make things faster, it unlocked the entire era of large language models and all the incredible new abilities that came with that massive scale. Let's climb to our fifth and, for now, final rung. We've got these incredibly powerful language models, but they're still, well, they're passive. They're amazing at predicting the next word in a sentence, but they can't actually do anything. They can't browse the web, or write a file to your computer, or call a program. They can only talk. They're brilliant brains in a jar. And this is the critical difference between a chatbot and a true AI agent. A chatbot is a passive responder. You talk to it, it talks back. But an agent is an active doer. The big shift is that you can give an agent access to tools, a web browser, a code interpreter, whatever, and it can decide for itself which tools to use and when to actually accomplish a goal you give it. And here's how it works, using a framework called REACT, which stands for reasoning and acting. It's a really simple but powerful loop. First, the agent reasons about its goal and what it should do next. Then it acts by picking a tool and using it. After that, it observes the result it got back from the tool, and it just repeats that loop. Reason, act, observe over and over until the job is done. This turns a passive chatbot into an autonomous problem solver. So, we've climbed the ladder, we've gone from AI learning basic patterns to an AI that can see, remember, understand language at an incredible scale, and now can even take action. So, what's the view like from up here? What's next on the road ahead? Well, the frontiers of research are just wild right now. You've got people working on world models, where the AI actually builds a simulation of the world in its head to predict what will happen next. You've got embodied AI, which is all about getting these models out of the computer and into robots. There's even neurosymbolic AI, which is trying to bring back some of that old school logic and combine it with the power of today's neural nets. And all of this is pointing toward what many people see as the ultimate goal: artificial general intelligence, or AGI. Right now, everything we have is ANI, or narrow intelligence. AI that's a genius at one or two things. The holy grail is AGI, an AI that's as smart and capable as a human across the board. That's no longer just science fiction. It's the focus of very active research today. So, to wrap up our climb really quickly, we started with symbolic AI, which tried to solve the problem of encoding human knowledge. Then, deep learning came along and solved the problem of automatically learning features from data. And finally, transformers solved the problem of parallelization and scale, which unlocked this whole modern era of AI. So I'll just leave you with this one thought. AI has learned to see, it's learned to read, and now it's learning to act. The next great frontier is foresight. So what happens when an AI that can already take action in the world also learns to accurately simulate and predict the consequences of those actions before it even makes a move? That's the question that's driving the next chapter of this incredible story.